What is going on in spaceflight? A Russian module docked with the International Space Station, then promptly began firing its RCS thrusters, spinning the entire station. Station thrusters and finally a docked spaceship had to fire their engines to counteract the force, eventually regaining control of the station. No permanent damage seems to have been done, but this emergency could have endangered the lives of everyone on board. What if the orbital maneuvering engines had fired, instead of the RCS engines? These more powerful engines could have torn the station apart. This near disaster delayed the launch of the Boeing Starliner spacecraft. It had been scheduled to launch to the International Space Station the next day. During the delay, further systems checks were ran on the Starliner. During these checks, it was found that valves for the abort system were not in the orientation being reported to the computer. This is an astounding problem to find after the scheduled launch time. The Starliner had just spent 19 months being reworked after a disastrous maiden flight in December of 2019. How did a ship that cost billions of dollars to develop come so close to launching with a faulty abort system? If the Starliner were to fail to abort during an emergency, or fire the abort engines at the wrong time during the mission, it could kill everyone on board the Starliner, and possibly the ISS itself. In light of this horrendous failure, should the Starliner be scrapped, despite all the money and time that has been spent on it? Welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please don't forget to like and subscribe, and help support us on Patreon if you can. There are links in the description. The CST-100 was announced by space entrepreneur Robert Bigelow in June of 2010. CST stands for Crew Space Transportation, and 100 may have been in honor of the Kármán line, which is 100 kilometers above the Earth's surface. NASA awarded Boeing $18 million to start preliminary development. The United States was looking for a replacement for the soon-to-be-retired space shuttle. The Starliner was selected to take humans back to space. It was supposed to carry crew to private space stations, like those planned by Bigelow Aerospace, and to government-owned stations, like the ISS. Let's take a look at what it takes to build a modern spaceship like this. The Starliner crew module with the service module attached is 5 meters tall. Here we see the components of the Boeing Starliner. We'll go through them one at a time. The ascent cover keeps the ship aerodynamic when it launches. Here we see a forward heat shield, an entry cover, parachutes, the reusable crew module. The Starliner was intended for up to 10 flights. We'll come back to the crew module in a moment. Landing bags, a base heat shield for re-entry, service module with thrusters and launch abort engines, and finally a solar array. Let's look more closely at how each of these are made. First, we start with the pressure vessel. We will contain the astronauts in a pressurized environment. While Apollo used a 340 millibar pure oxygen environment, the International Space Station is kept at normal Earth pressure, at 1.013 bars, and a normal Earth composition of nitrogen and oxygen. This is in case the station must be evacuated for an emergency. Astronauts won't have to pressurize before jumping in a capsule and heading home. Spaceships docked to the ISS will all be at the same atmosphere. You can see this pressure vessel being assembled here. This is called an isogrid pattern. This type of construction allows lower mass while still maintaining high strength. On the inside of the pressure vessel will go the seats and command panels. These are similar to what Boeing uses in its airplanes. It is almost always best to use something proven to be reliable over making something brand new. On the outside will go the airbag, seen here, that will deploy on landing. The Starliner can come down in water if it has to, but is intended to come down on land. Necessary external components like these reaction control or RCS thrusters seen here, are then installed outside the pressure vessel, with the wires and pipes necessary to make it all work. There will be a total of 12 RCS thrusters on the crew module, and another 28 on the service module. RCS thrusters make small changes to the ship's orientation. There will also be an additional 20 OMACs, or orbital maneuvering and attitude control thrusters. These are about 15 times more powerful than the RCS thrusters, and are used to make orbital changes. There are also 4 launch abort thrusters. These are extremely powerful, about 25 times more powerful than the OMAC thrusters. Once all the external components are installed, insulation is placed around the capsule. Then a protective outer layer is added. This outer layer must be resistant to solar energy exposure and micrometeorite impact. Here you see thermal blankets and ceramic tiles. The ship will come back to Earth at an angle, so one side will need more heat protection than the other. On the base, a heat shield will be attached. This will protect the ship during re-entry. Last, we get to the service module. Here you can see inside the service module, where there are tanks for the hypergolic fuel and oxidizer. This is 4.56 meters or 15 feet across. Finally, we see the abort thrusters again. There are 4 of these. These are Rocketdyne RS-88 engines for the launch escape system. This engine usually burns ethanol and liquid oxygen, producing 223 kilonewtons of thrust, but was modified to burn the hypergolic combination of monomethylhydrazine and nitrogen tetroxide, producing 177 kilonewtons each instead. This gives a total thrust of 708,000 newtons. Giving thrust in newtons can be confusing. It can be difficult to relate it to weight in our minds. If we divide by a bit less than 10, we can get kilograms. About 70,800. 1,000 kilograms would be a metric ton. That would give us roughly 70.8 metric tons of thrust. The crew module has a flight mass of about 8,500 kilograms with the crew. The service module is reported to be about 6,800 kilograms with propellant. That gives us a little more than 15,000 kilograms, or about 15 metric tons. If we compare the ship's mass of about 15 tons with the abort engine's thrust of about 70 tons, we can instantly see a thrust-to-weight ratio of almost 5 to 1. That should get astronauts to safety pretty quickly. This is not a bad design for a reusable space capsule. Several milestones were set by NASA for Boeing to achieve. After development, the Starliner would need to demonstrate a crew module mock-up, seen here, the launch escape system that the ship was planning to use. In addition, life support systems and autonomous rendezvous and docking would have to be developed and tested. Heat shield fabrication, avionics systems integration, and a landing system demonstration, which would be on land with the airbags seen here. The airbags were drop tested in 2011 and the parachutes in 2012. And finally, an abort hardware demonstration. Boeing assured NASA after this preliminary study that all of this could be accomplished and the ship would be operational by 2015. Boeing was awarded a $92.3 million contract in April of 2011 for Phase 2 development. In August of 2012, NASA awarded another $460 million. In September of 2014, NASA selected the Starliner and the SpaceX Dragon capsule as the 2 spaceships that would transport U.S. astronauts to and from the International Space Station. The SpaceX Dragon capsule had started making regular flights to the International Space Station in 2012. In 2015, NASA suddenly dropped plans to have Boeing resupply the International Space Station, but decided to give Boeing a $4.2 billion contract to complete and certify the Starliner for human flight by 2017. While SpaceX was given a $2.6 billion contract to do the same for the Dragon capsule. You may already see a problem here. If a company can't complete a cargo capsule on time, why would you assume it could complete a much more complicated human-rated capsule on time? By 2017, Boeing was already 2 years late on its previous contract, having received a total of over $500 million to have the cargo ship ready by 2015. SpaceX had an operational cargo capsule by 2012. We in the prime dimension are sometimes confused by governmental thinking in your dimension. Why would you pay more to a company that has failed to complete its mission? We do not argue that Boeing has not been a great company in the past. They have in fact done great things, helping to make America a leader in the aviation industry, and Boeing was instrumental to America's success in space, up to about the 1980s. Then something changed. Managers that had almost always had engineering experience were replaced by managers with none. The company went from taking pride in completing a contract on time or early to calculating how late they could be and how much more money they could charge. The brilliant engineers and hardworking staff were not allowed to build at their potential, while Boeing became terrible at making airplanes and spaceships. It became a master at making money, paying millions of dollars to lobbyists who passed legal bribes on to politicians, who then made sure that billions of taxpayer dollars would go to Boeing, no matter how badly they failed. Without competition, Boeing got lazy. But by 2012, Boeing had real competition. SpaceX was making rapid progress, and Boeing decided to actually try again. But while SpaceX had docked the Dragon capsule to the ISS in 2012, by May of 2016, Boeing was far behind, and had to delay its first flight again, from 2017 to early 2018, then again to late 2018. In 2018, a leak was found in the hypergolic fuel tanks. This was due to a faulty abort system valve. The abort system is a life-critical component of human spaceflight. To have such a major problem exist after so much development and testing indicated that something was terribly wrong. It was as if Boeing had forgotten how to actually build a good product. Boeing again delayed the first crewed flight from early 2019. Finally, in December of 2019, Boeing said the Starliner was ready to complete an uncrewed test flight. The ship was launched to orbit aboard an Atlas V rocket. Starliner was supposed to climb to the same altitude as the ISS and dock to the station, where it would deliver supplies and stay for 1 week. But the internal mission clock in the Starliner was off by 11 hours. Believing it was far away from where it was supposed to be, the ship started firing its thrusters to get into what it thought was the correct position. The ship burned so much fuel trying to make this unnecessary correction that it could not safely continue the mission. It was deorbited and landed at the White Sands Missile Range 2 days after launch. The entire fiasco was very damaging to Boeing's reputation, and they vowed to fix the problems. NASA went over the spacecraft and reported 80 problems that would have to be corrected. 19 months later, Boeing was poised to try again. But then the Russian module misfired, giving more time to check out the Starliner, allowing the engineers to find another catastrophic problem with the launch abort system valves. How was this not found in testing? Boeing and SpaceX show two vastly different thoughts on testing. Boeing starts off trying to design one perfect, extremely complex spaceship. They try to anticipate every contingency, and by the time something is built, they have spent too much on it to risk damaging it in testing. Boeing counts on everything working as it does in simulation, with very limited real-world testing. While SpaceX understands that calculations and simulations will only find the problems you already know about. The solution is rapid prototyping and testing. Build it, fly it, crash it, fix it, and fly it again. Each component is assembled with the minimum necessary to get the job done. If it works great the first time, see if there are components you can remove or simplify. This method also has its detractors. You have to suffer the media loudly announcing every crash. This is painful, but necessary to build a robust spaceship. At this point, I think the Starliner is not safe to be considered for human spaceflight, or even docking with cargo to the ISS. Boeing would have to start testing them over and over again to work out all the mistakes. I don't think they can afford to do that. A major difference between these two companies is that while Boeing is a publicly traded company, answerable to the whims of investors and the stock market, SpaceX is a privately owned company, answerable only to the king. More short-sighted people will cry about how the money could have been spent better here on Earth. And this makes all the difference. No sane investor would put money on colonizing Mars. The benefits are very long-term. But if we succeed, our grandchildren will revere us for the sacrifices we made and the worlds we give them. Thanks for listening. Please don't forget to like and subscribe, and help us out on Patreon if you can. At Astra Pro Terra.